All right. Good morning. Okay, so we're going to start our newest topic, which is solving nonlinear systems. So we just finished up talking about our linear systems with three equations and three variables, x, y, z. And so now we're going to move on to nonlinear. We're going to start that today, and I'll show you a couple examples. This is going to be slightly shorter, as the stream title says, because I have to go to or I have to attend a virtual meeting starting at 8:30. So a couple minutes before then is when I'll go ahead and stop. But we'll at least get the main idea out there and show a little bit of what it looks like. We'll go from there. So a nonlinear system of equations. Okay, so when I talk about nonlinear, so that means we're also going to have quadratic terms. All right, like x squared and y squared. Okay, so for example, talking about having equations like our conic sections that we dealt with earlier, hyperbolas, parabolas, ellipses, circles. Those we'll be talking about the general forms of those equations and solving for what the solutions are. As far as our methods go, we're still using what we've done before. Right? Substitution, if we can. And if we can't do that, or if it's not practical to do that, then we'll use elimination. Again, just like we did before, where we get those matching terms on the same variable, the positive version, the negative version. That way we can then cancel them when we add the equations together. Right? So the methods have not changed. It's just what the equations have looked like. When we solve these, we're going to get up to 4 solutions, depending on the problem. So I think it was Jacob that asked in the last class, what are the different options? So usually, well, for linear systems, we always end up either with there's 3 choices. We can end up with one single solution, we could end up with no solutions, or we could end up with infinitely many solutions. Unfortunately, for nonlinear systems, that isn't exactly the case. We could end up with one solution, we could end up with 2, we could end up with 3 or 4. So it's kind of much less grounded of, do I know an idea of what I should end up with here? Okay, so we have to be a little more careful, a little more diligent. I could write more about the specific steps, but that's the general idea. I guess an important thing, since we can get multiple solutions, don't just stop after you get one solution. If you have more values. Okay. So if we're doing our solving and we have multiple x values, well, don't just take that one of the x values and plug them into the equation. Okay, we have to take both values and plug them into the equation eventually. So don't just stop at one. Let's take a look at our first example. This is kind of a more basic example. X squared minus x minus 1, or x squared minus x minus y minus 1 equals 0, and 3x minus y minus 4 equals 0. Okay, so we can see that first equation is nonlinear. It has that x squared term in it. So, but the other thing that I notice when I want to go through and solve this, so if I'm choosing, we always hope probably we can do substitution just because that's usually an easier version of doing things. And I noticed that this y just has a coefficient of 1, or technically -1 here. So I think I can see that it would be easy for me to just solve that equation for y and then plug it into the other one. So solving by substitution. So I'm just going to add y to both sides. So 3x minus 4 equals y. So just adding y to both sides. From there, I now have an equation that's y equals. So I'm going to take, I'm going to take 3x minus 4, and I'm going to substitute it back into my first equation for y. Okay, solving by substitution. So let me do that. X squared minus x minus 3x minus 4 minus 1 equals 0. Super important. Make sure you, when you substitute that equation in, oh, what is going on? That you put those parentheses around the 3x minus 4, because whatever the original coefficient was, in this case just negative, will get distributed. So let's do that now. Let's distribute. X squared minus x minus 3x plus 4 minus 1 equals 0. You're running out of ink. I know. Now that we're doing virtual learning, I'm running out of virtual ink so fast. Like, you gotta really shake it a lot. It's tough. Let's combine some like terms. So x squared minus 4x plus 3 equals 0. So I'm solving. I have a quadratic now equals 0. Great. So now going back to the very beginning of the year, we talked about all of our methods of solving for quadratics that we can do. Factoring, completing the square, using the quadratic formula, but the quadratic formula sucks. So hopefully we don't have to use that. But I'm looking at this one, and this is something that I can just factor. All right, looking at my two numbers here. So I just need two numbers that multiply to make 3, but add together to make -4. So that would be x minus 3 and x minus 1. So if I set each factor equal to 0, for the first factor, I would get x equals 3. For the second factor, I would get x equals 1. Okay, so I'm definitely going to have more than one solution here because I have two distinct separate x values. I have an x value that's 3. I have an x value that's 1. So I need to figure out y. I'm going to first go back in and plug in 3 and figure out what the y values are. And then after that, I also have to go through and plug in 1. All right, so I'll do two cases. The first case, I'll plug in 3. The second case, I'll plug in 1. So the easiest way to do that would just be to use my equation for y that we have up here at the top, 3x minus 4 equals y. So y equals 3x, but we're saying x is 3. Wait, was it 4? I already forgot. 3x minus 4. Yep. So 9 minus 4 is 5. Okay, so again, this is our first case. We plug in the first x value we got. So one of my answers is 3, 5. That's one solution. Okay, now separately, right, this is what I'm saying. A lot of people, they mess up because they stop now. They got 3, 5 as their answer, and they think, okay, I just solved there. Or sometimes people will also put an answer of 1, 5 just because we have the 1 over here as well. But that's not the case. Okay, don't do that. So we have to take 1 and plug it in separately to our equation. So y equals 3 times x, but now we're doing x equals 1 minus 4. So 3 minus 4, negative 1. So now I plug in if I plug in 1, the y value that I get is negative 1. Okay, so I have to plug in both x values separately to whatever the equation is. And these are my 2 answers. So this is a problem where I get 2 solutions. Okay, let me pull up Desmos really quick, just to visually show what the heck's going on. Okay. My original equations, x squared minus x minus y minus 1 equals 0. And 3x minus y minus 4 equals 0. Okay, so it creates this graph. And I can see these 2 curves, well, one's a curve and one's a line, intersect in 2 points. And what are those 2 points? Well, 3, 5 and positive 1, negative 1. Those are exactly the points that we just solved for. Okay, so that's what we're doing when we solve this system. We're saying this equation and this equation, where do they meet? Where do they intersect on a graph? Okay. And since now we're talking about non-linear, so since we can now have things that are curved, like a parabola like this one, or maybe a circle, so there's a lot more opportunities for things to intersect, which is why we could end up with 2 points or 3 points or 4 points. Okay. So that's exactly what we have. Bring this back down. Okay. 8:15. Great. Let's try our next one then really quick. All right, I want to get through this one. That'll probably be the last one we do for today. So I have these 2 equations. I probably don't want to solve this for substitution. Now, for the last one, this was nice to solve for substitution because not only was the coefficient of y just negative 1, but this equation that I just circled also doesn't have a quadratic term in it. It doesn't have an x squared. It doesn't have a y squared. So it made it really easy that when I plugged in 3x minus 4, I didn't really have to do a lot of work. I just had to combine a couple like terms, and then I got down to x squared minus 4x plus 3. But these two equations have a lot more going on. They both have a y squared term. They both have x. They both have y. They both have constants. So I don't know. If we really wanted to, we could solve this through substitution. But I'm going to show you what it looks like from doing it by elimination. So for elimination, right, our same idea. We want to eliminate some variable. Now, in this case, whenever we're doing elimination, we want to eliminate so that we have all x's or all y's. Okay, eliminate so that we have all x's or all y's. So that means I'm going to choose to eliminate x in this equation, because then I'll be left with y squared and y. I don't want to have a mix. I don't want to eliminate y, because then I'd have an equation that has y squareds in it and x's in it, which doesn't help me as much. So right now I have positive x and positive x in both. So I'm going to choose one of these. It doesn't matter which one. And multiply it by -1. And I'll put that down here. So that would be positive y squared minus x plus 11y plus 30. 0 times -1, 0. Or -0, you know. Could you divide everything by 2 and eliminate y? Yes, you could. However, then you still have a mix. If you eliminate the y term, then you'd have... Oh, are you saying because it would eliminate both y's? Is that what you're trying to do? In this case, that would work, but again, we'd have to make sure that it would need to eliminate both. So if it eliminates both the squared term and the linear term at the same time, then yes, you could do that for sure. Right, but otherwise, we just want to stick to either all x's or all y's, because it won't always work out that it would get rid of both of them. But you could. Yeah, that's a good point. This second equation, I'll just write that again. And then add together. 3y squared, negative x plus x is 0, plus 33y plus 90 equals 0. Okay, so now I have a quadratic that I want to solve. So now I'm just trying to, this is set equal to 0. I want to solve for y. Again, we have our various methods that we can solve quadratics by. But I'm going to try, I always start out with factoring. I have a GCF here of 3, so let me pull out 3. Plus 11y plus 3 equals 0. Y squared plus 11y, wait, not plus 3. That's not 9. Come on. Plus 30. I do know math sometimes. Multiplies two numbers that multiply to make 30 and add together to make 11. y plus 5, y plus 6 equals 0? Sometimes. Set each factor equal to 0, y equals -5, y equals -6. I would not have y equals 3. Right? I know that people see the 3 here and then want to put y equals 3, right? But that's not the case. What we're doing is setting each factor equal to 0. So y plus 5 equals 0, that's why I get y equals -5. Y plus 6 equals 0, that's why I get y equals -6. If I set 3 equal to 0, that's nonsense. 3 is not 0, so I don't get anything from it. So I'm not even going to write it. Okay, so I'm going to do my two cases now because I have two y values, and I'm going to plug those back in to solve for x. We can choose either equation to do that in. It doesn't matter. I'll do the second equation because why not? So 2y squared, so 2 -5 squared plus x plus 22y, so plus x plus 22y, so that's -5, plus 60 equals 0. I'm just going to take some simplification. So -5 squared is 25. 25 times 2 is 50. Plus x plus 22 times -5. 20 times -5 is -100. 2 times -5, -10. So that would be minus 110. And then plus 60 equals 0. And actually, so 50 plus 60 is 110. So -110 plus 110. Those actually all cancel each other out. So I get x equals 0 for my first solution. So my first solution's point is -5, or no, sorry, not -5. Remember, because the x value goes first, so 0. And then the y value that I plugged in to get that was -5. So 0, -5 is one of my solutions. And now I want to do the same thing, but with -6. So I'm going to plug in -6. 2 times -6 squared plus x plus 22 times -6 plus 60 equals 0. So it was just plugging it into that same second equation. We could have chosen the first or second equation, but I just kept it like I did before. 6 squared is 36. 36 times 2, 72, plus x, 22 times -6, -132. Come on. There we go. And plus 60. Equals 0. And interestingly enough, so 72 plus 60 is also 132, -132 plus 132. So these all cancel as well. Leaving me with x equals 0. So also I have 0, -6. So these are my two solutions. Okay, don't always expect that you'll get the same value. So for this problem, it just so happened that we got x equals 0 for both of them. Okay, but don't expect that. Okay, always plug in each individual y value to see what it ends up looking like. So I'm going to scroll it for a second and I'll scroll back down. Come on. Sorry, I'm trying to graph this really quick to show. Negative y squared plus x minus 11y minus 30 equals 0. And two y squared plus x plus 2y plus 60 equals 0. Let me pull this up. Okay, so I entered in my two equations. So these look like this, right? These two parabolas. And I can see they are intersecting in 2 points. Let me zoom in. So what are those 2 points? 0, -5, and 0, -6. Okay, which is that same value that we just solved for both of them. Right, so that's exactly what we're doing, is we're solving for where these two values intersect. You're mumbling. I never mumble. Ever. Okay, so I know that was fast. Hopefully it made a bit of sense. And again, we're going to talk about this more on Monday. I have to get to my meeting. So we talked about on Wednesday. Today technically isn't an A day. It would have been. Monday was an A day, but then Tuesday was going to be super test day with the ACT. So it skipped. So technically today is a B day, but next week we'll still be on track with, so the plan is to be on track with when normal A days are. So next week that'll again be Monday, Wednesday, Friday. So we'll go Monday, Wednesday, Friday next week. The actual A days, even though we slightly got off this week because I forgot about the ACT day. But I will go to my weird teacher meeting. All right. So let me know if you have questions, or come to my office hours later. But I will see you guys on Monday.